So welcome back to a new video, and today's video we are going to electrical circuits. So we have done the chapter thermoelectric effect before this one, which was a short one and is also very important. I said that in the last video, and now we're going to chapter 2, which is electrical circuit, and we are simply starting off with Kirchhoff's law. So let's start off. Alright, so in the first place we are doing Kirchhoff's law. There are two laws in this section, and we are starting off with the first law. In the number 1 we have first law, which is also called Kirchhoff's current law. What is it? Kirchhoff's current law, or it is also called junction law. What does this law say? It is a very simple law here. This states that at a junction of an electrical circuit, the algebraic sum of currents is 0. Mathematically, this means that at a junction, sum of I will be equal to 0. Imagine there is a junction just like this, and the one current I1 is going in from here, a current I2 is coming in from here, a current I3 is coming in from here, and the current I4 is going simply there. So the sum of currents in this point, will be equal. Oh, this is not possible, my bad. Let's go like this. Yeah, this right there in this point A, the current is 0. That is all you need. And about the sign convention, you know that if this is going opposite and this is going this side and this is going this side, this is going this side. So if we need to declare the sign convention, we can just take one side as positive and the other side as negative. For example, how do we do it? Is two currents I3 and I1 are going in from here and two of them are going out. So it will basically be I3 plus I1 minus I4 minus I2 will be equal to 0. Or if you take this one as positive, then you can just take I3 minus I1 plus I4 plus I2 will be equal to 0. This is all you need to know about sign convention. Now let's go and move to the second law of Kirchhoff. So to go to Kirchhoff's second law, we have to know its names. And wait. Right here, you need to remember that it follows the law of conservation of charge. This law follows the law of conservation of charge. So yeah, now we're moving on to the second law, or Kirchhoff's voltage law. It is also called Mace law, also called loop law, and there are many others laws, many other names for this. So yeah, you know it, right? So what does this state is that in a closed loop of an electric circuit, the sum of EMFs is equal to the sum of product of current flowing through it and the resistances in the loop. So what I'm saying right here is, this states that the EMF, or the sum of EMF is equal to the sum of product of current and resistances along the loop in a closed loop. So what are the necessities here? To apply second law of Kirchhoff's, the loop must be closed. That means in an open loop like this one, Kirchhoff's law cannot be applied. So a loop has to be closed like this to apply Kirchhoff's law. You have to understand that first, and after that you need to understand what does this mean. Sum of product of current and resistances. This mathematically means the EMF sum will be equal to the sum of product of current and resistances. That's all you need to know. About the sign convention is a bit different here. Imagine a closed loop like this, and there is a battery cell just like that. Then you can take the direction yourself. For example, there is given the current is flowing like this, current I, and the battery is E. So to take the direction, you choose it yourself. For example, if I choose the direction like this, that is anti-clockwise, then while I come here, the direction of I right here, look at this, let me put a resistance right here, okay? Let me put a resistance right here, right here, right here. There will be I2, I3, I1. So what happens right here? What happens is this is opposite direction. There will be R1, R2 and R3. Then the current, the direction we chose is opposite in direction. Are you getting the point? It is opposite in direction than what the current is going through. And right here, look at this. We chose the direction like this. So it's again opposite here. Look at this. While we go up here, it will be like this, and while we go back, it will be like this. So the current here is flowing like right here, and we are going opposite to it. So this will also be negative. And right here, it is positive because it is going down, and we are also going down. Look at this. We are choosing this direction. We are going like this, and this is also going down. So we are correct in this one. So after that one, you check the direction of the E. We chose the anti-clockwise direction. So what happens is we go in from the positive terminal of the battery and get out from the negative. That means from what we get out, that will be the final direction or the final magnitude, final direction of the EMF. So what here happens is, since this is the relation, sum of E, there is only one E, so this is negative, will be equal to IR. I is I1, sum of I is I1, I2 and I3, right? So I1 here is negative, so I1 R1. I2 also is negative, so I2 R2. But this one is positive, so I3 R3. That is what happens, and this is the final relation, and this is how you solve it. That is the whole thing of Kirchhoff's second law or Kirchhoff's voltage law. Now we're moving towards the next topic right here, and that is the numericals related to this. But since I've already done one, and that's how we do it, I'll just do only one numerical, because every single numerical is exactly same. You do the exactly same thing in every single numerical. It's just the number of process, and it's just a bit longer or something. So I'll just do one very important numerical, and which will be enough for you all to revise and understand it. And if you don't understand, you can still message me or comment down in the video. So yeah, we can go for it. Okay, so the question I chose is like this. Let me draw the figure that's given in the question. Oops. That's it. This is the question, and there is given some directions. This is I1, and this is 60 ohms, this is 200 ohms, this is 20 ohms, this is 5 volt, this is the negative terminal, this is the positive terminal, negative, positive, I1, B, A, and that is everything that's given. Okay, and there is I1, is I3, and this is I1, this is I2. That's what the question gave. Okay, so now this is 4 volts. First, if you don't know, the shorter line of the battery means that's the negative terminal. So the electrons will flow from all the way here to there, but the current will flow from right here to here. That's how it happens. So now we need to solve this and find the values of I1, I2 and I3. This is a typical question. This is a typical question. Questions like this will 100% be asked in your final examination. So you better understand this topic, and if you don't understand in this video, it's alright. There are many videos in the YouTube, so you can take the reference from those videos and do it. But I'm not going to what do I say? I'm not going to like use a lot of things here, so I'm just going to explain thoroughly. If I take direction anti-clockwise, which you can take in any direction, then what will happen? Let's see. Let's take a loop. First of all, let's use the first law. In every numerical like this, generally you use the first law. So first you can write from Kirchhoff's current law. What do we have? At a junction B, we know that these two, look at this, there is 0. So we can just write I1 and I2 are in the same direction, but I3 is in the negative direction, equal to 0. That will be I3 will be equal to I1 plus I2. We know that, right? So we can give this equation 1. After that, what we are going to do is use the second law in this loop. So let's take a loop. Take loop ABDA from Kirchhoff's voltage law. We know that, what do you know? We know that the sum of this one is equal to the sum of all that, right? So here there is only one battery, so there is only one EMF, and the sign will be positive because it enters from the negative and exits from the positive. So you can just simply write down E is equal to, or you can just simply write 5 equal to, we go down, I1 is correct, I3 is correct. So both of them will be positive, and what will happen is I2, the current I2 here, look at this, the current I2 has flown such way that it has come through this resistance. There is no other distribution from here to here. So the current of this resistance flowing through this resistance is I2, because I3 may get distributed right here. So but I2 is very sure that it has come from here. So what do you write is I3. Okay, so I2 into 200 plus I3 into 20 IR, just like that. And then we just put the value of, okay, no, we just keep this equation. Let's find the value of I3 though. Okay, so 5 minus 200 I2, 5 minus 200 I2 by 20 will be equal to I, or you can take 5 common and cut down. So 5, 1 minus 5 4 is 20, and that will be 5 by 5, let's do it, and 5 4 is 20 equal to I. So you can cut this and put this equation 2. So we know that I2 will be equal, I3 will be equal to that times that value. So now we again take the other closed loop. This is the BDC. We take the loop BDC just like this. Look at this. In loop, at a loop BDCB. What do we have here is, this will be negative, this will be positive, this will be positive. Okay, so yeah, look at this. If this comes here, then this will come down here, so it will be negative. So I1 minus I1, okay, minus 4 will be equal to minus I1 into 60 minus I3 into 20. So we have minus 4 will be equal, okay, you can just take minus common, so 4 will be equal to 60 I1 and and plus what will happen is I3 into 20 will be, let's not put the values right now. So that's it, and we take 4. Can we take 4 common? I think yes, so let me use a calculator. Yeah, we can take 4 common, so 1 will be equal to 15i1 plus 5i3, and we can put the value of i3 as well. i3 will be equal to, in terms of i1 only, right? Oh no, we have an issue here. To solve this, look at this. i3 we know as well, but we cannot put any of them because this will again give 2 things. So from equation 1 we have to find the value of i2, where is it, i2 in terms of i3 and i1, you get me? And then we can do it. So first let's get the value here. i2 will be equal to i3 minus i1, that's i2, and now we can put i2's value right here. Okay, no, we cannot do that, bro. Okay, you can basically solve for this. Let's just find i3 again. 5i3 will be equal to 1 minus 15i1, and i3 will be 1 minus 15i1 by 5. Since this and this are equal quantities, what do we know, that this and this also will be equal, so we cannot, okay. Okay, yeah, but you can do all this, but you can basically use a calculator to solve all this. You can just put the values of, I think I missed some signs and all, but this is solvable. But you don't have to do this in an exam, so you can just get the equations and then use the calculator to solve all of them. So if I use my calculator, the 3 equations, I just go to mode, in this Casio FX991 ES Plus, I just go to mode 5, and then I need to solve a linear equation with 3 variables. So I have, look at this, the 2 is the thing. For a first equation, 1 minus 1 and 0, yep. And for the second equation, we need to find what is the second equation. Yeah, look at this, 5i1 is 0 in second equation, right? So 0i1, and look at this is 200i2, and this is 20i3, and this is 5. For the third equation, third right here, third equation, you can just use this part here where i2 is 0. Can you see this? Look at this. You can use this part of the equation in the calculator. So i1 is 15, i2 is 0, i3 is 5, and the other thing is 1. If you solve this equation, you get the values, and you can just simply write them in the answer. And that's how we do it. Solve. Yeah, now we are moving to the next concept, that is Wheatstone bridge, which is the most important thing in this chapter. Wheatstone bridge is very, very important. So you need to know about Wheatstone bridge, and then we will do one numerical regarding Wheatstone bridge. Then we go to meter bridge, and then we go to the most important another thing, potentiometer, and we learn its 3 major applications, which are very, very important again. And we do some numericals regarding to it, and we convert the galvanometer and all the things in that using it, and then that's over. So yeah, for this video I'm ending it right here, but in the next video we're gonna do Wheatstone bridge and potentiometer completely. So yeah, stay tuned till then. Peace out.